Hello, this is Dr. Hanaa Assil, and this is paper 6-1 of June 2017. This is the Cambridge IGCSE chemistry. Let us take a look at the questions. So the first question in this paper, of course, paper 6 is the alternative to practical. The question says, a student prepared strontium nitrate crystals. The diagram shows some of the stages in this preparation. So he has stage 1 in which strontium carbonate was added to acid. Then stage 2, he's stirring the mixture. And then in stage 3, he has the strontium nitrate solution that he was trying to prepare and unreacted salt. Complete the box to identify the apparatus. What is that apparatus that we stir a mixture with? It is called a glass rod. What is used to add the strontium carbonate to the acid? When I want to add a solid to acid in a beaker, we use what? You should realize that we use a spatula. Name the acid used. What is he trying to prepare? He's trying to prepare strontium nitrate. So he's going to react strontium carbonate with what? Nitric acid. In order to get nitrate, we're trying to prepare strontium nitrate. So we're going to react the carbonate with acid. Give one expected observation in stage 2. What do you expect to see when you add carbonate to acid? Any carbonate with acid will give carbon dioxide gas, and that means what is the observation? Don't say carbon dioxide gas. Observation means what am I going to see? I know that it's going to give carbon dioxide gas. That means I'm going to see what? I'm going to see bubbles of gas, or you can say fizzing. Which of the reactants is in excess? Okay, remember that this is a method of preparing salts. And you know that we have 3 methods of preparing salts: titration, neutralization, and precipitation. Which method is this? You should realize that this is the neutralization method, in which the solid I'm adding is in excess. So the strontium carbonate, when we added it to the acid, I have unreacted solid at the bottom. The solid is stirred, but some of it will react, and then I keep adding strontium carbonate until I have excess solid in the beaker. So the excess here is the strontium carbonate because solid remains in the beaker. Then he says, describe how crystals of strontium nitrate could be obtained from the mixture in stage 3. So in stage 3, I have what? I have unreacted solid and strontium nitrate solution. Now, how do I get crystals from this solution that has excess solid at the bottom of the beaker? Remember, I'm starting with excess solid at the bottom of the beaker. So the first thing I should do is filter to remove the excess solid. And then I take the filtrate. Now that is strontium nitrate solution. I should do what? I should do crystallization. So this is what I explained to him, that he's supposed to filter the mixture through filter paper and funnel, and then heat the filtrate to point of crystallization, cool to form crystals, then filter the crystals. This is how you obtain crystals from a solution. This is, of course, crystallization. Okay, question 2 says, a student investigated the reaction between aqueous sodium thiosulfate and 2 different aqueous solutions of potassium iodate labeled solution C and solution D. So we have sodium thiosulfate with something called potassium iodate. I have 2 different solutions of that. One we're going to call C and the other D. 2 experiments were carried out. In experiment 1, a burette was filled with aqueous sodium thiosulfate. So the sodium thiosulfate is in the burette. The initial burette reading was recorded. Using a measuring cylinder, he added 20 centimeter cubed of solution C into a conical flask. 10 centimeter cubed of dilute sulfuric acid, 1 gram of potassium iodide were also added to the flask to form a solution of iodine. So we're starting with iodine. The flask was swirled to mix the contents. Aqueous sodium thiosulfate was slowly added from the burette to the flask and swirled to mix thoroughly. When the contents of the flask turned pale yellow, starch solution was added and the solution turned blue-black. Remember that the solution has iodine, and you should know that when we add starch to iodine, or the other way around, if we add iodine solution to starch, this gives a blue-black color. More aqueous sodium thiosulfate was then added slowly to the flask until the solution turned colorless. Of course, when the solution turns colorless, then all the iodine has been used up. The final burette reading was recorded. So remember that in a solution, when we have iodine in the solution and I'm doing titration, I don't need to add an indicator because what we add is starch solution. So in this case, the starch solution is acting as an indicator because starch with iodine gives blue-black, and then I add until the blue-black color disappears. So anyway, here we have used the burette diagrams to record the readings in the table and complete the table. Notice that the first one he has there is final. The main mistake that many students do, they put the initial in the place where they're supposed to put final and the other way around. So the first reading in the table that I'm supposed to record here is my final. Where is the final burette reading? Of course, the burette is read from up to down. Or in general, we read burettes or we read measuring cylinders from the small number to the big number. So here the small number is on top. So this final reading is 38 point something, not 39 point something. So this is 38 point what? This is 38.3. I'm going to remind you again that you do not put units again inside the table. It is already written there. He says final burette reading in centimeter cubed. So don't go and write 38.3 centimeter cubed. You don't write that again. Then the initial burette reading. What is the initial burette reading? That is 4 point something. So this is 4 point what? This is 4.1. Of course, the difference is the final minus the initial. So in this case, the difference is 34.2. Then he says experiment 2, the conical flask was emptied, rinsed with distilled water, and experiment 1 was repeated using solution D instead of solution C. Now, use the burette diagrams to record the readings. What is my final burette reading here? My final is 20.8. And my initial is what? 3.7. So the difference is 17.1. And then he's saying which solution of potassium iodate is more concentrated. Remember, he says solution C and D are potassium iodate. Which one is more concentrated? Well, let's look at the results. Now, solution C took 34.2 of the thiosulfate. Solution D took 17.1 of the thiosulfate. Remember, if we have a solution in the flask, the more I need from the burette, the more concentrated is my solution. So C needed 34.2, so C is the more concentrated solution because it needed more of the sodium thiosulfate to react with it. How many times more concentrated is this solution? Well, let's see. Solution C took 34.2. Solution D took 17.1. 34.2 is about twice. Actually, it's exactly twice, 17.1. So that means that C is twice as concentrated as D. Are we following? Okay. Predict the volume of aqueous sodium thiosulfate, which would be needed to react completely with 30 centimeter cubed of solution D. Now, that first reaction or that first experiment was using 20 centimeter cubed. And when we used 20 centimeter cubed of solution D, I needed 17.1. Now he's saying I'm going to use 30 of solution D. How much should I need of the thiosulfate? Well, cross multiplication, that's how we normally do it. So the 20 needed 17.1, so the 30 will need how much? That is 30 times 17.1 over 20, so it will need about 1.5 times what we got for solution D. So that's 25.7 centimeter cubed. Okay? State two sources of error in the experiments. Of course, when he asks me about two sources of error, I go back to the experiment and I see what did he do in the experiment. Well, one thing he did was using a measuring cylinder, he added 20 centimeter cubed of the solution to the conical flask. Is that accurate? Actually, we said measuring cylinder is not accurate, so using a measuring cylinder to measure the volume of the solution is not a good idea. This could be a source of, and of course the fact that he did the experiment only once. So just two improvements. So instead of using measuring cylinder, how can I improve it? I can use either a pipette or a burette. And the fact that he did the experiment only once means we're not really sure the results are correct, so we should repeat and take average results. Question 3 is about identification of ions. He says two solids E and F were analyzed. He's telling me that solid F is potassium iodide. Tests were carried out on each solid. Some of the observations are shown. So the first thing he's saying, solid E. Appearance of solid E is a green solid. Now, what does that tell me? If he says that the solid we're talking about has any sort of color, green, blue, brown, black is regarded as a color, any of this tells me that the solid has transition metal. So if it is colored at all, it has a transition metal. If he says it is a white solid or a colorless solution, then that means I don't have a transition metal. Then solid E was heated gently, then strongly, and the solid turned black. Okay, that might give me an indication that yes, we have also a transition metal. Then in test 2, he says dilute sulfuric acid was added to solid E and the gas given off was tested. And what he got was rapid effervescence, lime water turned milky. Now, if I add acid to something and the lime water turns milky, what does that tell you? It tells you that I have carbonate, because when I have carbonate, I add acid. It will give carbon dioxide gas that turns lime water milky. So this test tells me that we have carbonate. Then he says excess aqueous ammonia was added to the mixture. What did he get? A pale blue precipitate, which dissolved to form a dark blue solution. Which ion with aqueous ammonia will give a pale blue precipitate that dissolves to form a dark blue solution? You should realize that this is test for copper 2. So this means that we have copper 2 ions. Then he did a flame test. Well, when he did the flame test, he got blue-green. And you should realize that blue-green confirms the fact that we have copper 2 on. So, where are the questions? The first question says, test 1 states that the solid should be heated gently, then strongly. In terms of safety, explain why it is necessary to heat gently at first. So you should know, if I'm heating a test tube that has a solid in it, I should first start to heat it gently and then a little bit strongly. Why is that? Because if I heat it strongly at the beginning, then the solid will, what we call, spit out, or it will jump out of the test tube. So why are we heating it gently? So that the solid does not spit out of the test tube. Or you could also say, well, we're heating it gently so that the test tube does not break. Then he's saying, identify the gas given off in test 2. Which one was test 2? I go back and I look at test 2, and this was the test that gave off rapid effervescence and the lime water turned milky. And we said, which gas will turn lime water milky? Carbon dioxide gas. That is correct. Okay, then he's saying identify solid E. First of all, the word identify means give me the name, or give me what it has. It has what and what, or its name is what. So we go back to the tests that he did. He did a test that showed that we had carbonate when he added acid and we got carbon dioxide. He did 2 tests, aqueous ammonia and flame test, that confirmed that we have copper 2. So what is my solid? My solid is copper 2 carbonate. Or you could say it has copper 2 and carbonate. But then the solid, if it has these 2 things, then it's called copper 2 carbonate. Okay? Tests on solid F. Okay, what did he say about solid F again? He said solid F was potassium iodide. So we're talking about potassium iodide. Describe the appearance of the solid. What does he mean? He means, is it white or does it have a specific color? Well, we look at it. Does it have a transition metal? Is potassium transition metal? No, potassium is in group 1. No transition metal, then my solid is white, no color. So we call it white solid. If it were a solution, again, we don't say white solution, we say colorless solution. If it's a solid, no color, it is white. Then he says distilled water was added to solid F in a test tube and shaken to dissolve solid F to the first portion. So again, remember, we have potassium iodide. To the first portion of the solution, and excess sodium hydroxide was added. What is the observation? Do you remember the test that we did with excess or with aqueous sodium hydroxide? Did we do tests for potassium? You shouldn't get any result because this will form potassium hydroxide, and that's just a solution, colorless solution. So what you see is no change. Because when you add sodium hydroxide to potassium iodide, what do you get? You get potassium hydroxide and sodium iodide. Both of these are soluble salts. So no change, everything is still colorless solution. Then to the second portion of the solution, dilute nitric acid and silver nitrate were added. So the first thing you ask yourself, silver nitrate is test for what? You should realize that silver nitrate is test for halides, chloride, bromide, iodide. If I have chloride, it should give me white precipitate. If I have bromide, it should give cream precipitate. If I have iodide, it should give yellow precipitate. Which one do we have? We have iodide, so it should give yellow precipitate. Please write the spelling of precipitate correctly. A flame test was carried out on solid F. Again, what was solid F? Solid F was potassium something. So if I do a flame test for potassium, do you remember the colors? You should know these colors. These are the colors for the flame test. Please notice that barium and, barium is an addition to the new syllabus. So we had lithium gives red, sodium yellow, potassium should give what? Potassium gives a lilac flame, calcium gives what we call a brick red or orange red, barium gives green, or sometimes they call it apple green or light green, copper gives blue green. So please learn these colors. Potassium gives lilac. Describe how you would carry out a flame test. How do we do a flame test? You should remember that the first thing we do is clean a platinum wire by dipping it in concentrated hydrochloric acid. So clean a platinum wire by dipping it in concentrated hydrochloric acid. Then we dip the wire into the salt, and then we expose the wire to the non-luminous flame of the Bunsen burner. So that's the part that does not have a color. Non-luminous flame of the Bunsen burner, and observe the emitted light. So this is how we do a flame test. Please learn this. A sample of furniture cleaner contains aqueous sodium chloride, aqueous ammonia, and sand. Give a test to show the presence of ammonia in the mixture. Okay, sometimes he asks test for aqueous ammonia or test for ammonium ions. He's here just saying test for ammonia. Of course, if my solution has ammonia in it, then it should be alkaline. And that means if I insert red litmus, it turns to blue. Plan an investigation to obtain a sample of. So he's saying I have water and sand and sodium chloride. Was it sodium chloride? Yes. And ammonia and sand. So we're trying to plan an investigation to obtain a sample of pure water from the mixture. Now, if I have a solution that has many things and I want the water, how do we get the water from a solution? We should use simple distillation. But he's saying plan an investigation, so we're going to explain to him what is simple distillation. We're going to heat to boiling in a flask connected to a condenser. The vapor is cooled and condensed in the condenser to be collected in the flask. So we get the pure water. What if I want from my mixture, I want the sand? Of course, the sand is something that is not soluble, does not dissolve. So it's a solid in the beaker. So what we do is filtration. He wants pure sand, so I'm going to explain to him that we're going to filter the mixture through filter paper and funnel, wash the residue with a few drops of distilled water, dry between filter papers. And that's the end of this paper. I hope you understood all the questions. Please share the video with your friends, and thank you for listening.